As mentioned in the last example of the previous lecture, this particular point 4 is what we call an equilibrium and is really of very special interest because we will be thinking a lot about how the solutions behave if they tend toward a particular point or run away from it. We would like to introduce some useful terminology to be used throughout. So first of all, this is a definition you likely have seen in your biology and chemistry courses. If the system is not changing, then that state is called a steady state or an equilibrium. And we will be using those two words interchangeably. In our setup, we can also define the steady state as the points that satisfy this particular condition. Y prime is equal to 0. That is, of course, because remember that y prime is the rate of change of y, and if it's not changing, then the rate of change of it is indeed equal to 0. Any steady state is going to satisfy this particular equation, any and every steady state or equilibrium. We will identify two different types of steady states themselves. One is going to be called stable and one is going to be called unstable. A steady state is called stable if its states that are initially a steady state is called stable if states that are initially close enough to that state will get even closer to it with time. So stable states attract the points around it. A steady state is called unstable if states that are initially close to it will move away from that steady state. So the unstable steady state wants points to run away from it. One analogy that I find useful is an analogy of a cup and a marble. So a stable steady state is like having a cup that's facing sort of the right way or concave up. A steady state here is the state right on the bottom. And that's because if I drop a marble into the cup, it will come to rest right at the bottom of the cup. It is stable because if I drop a marble, the marble will get attracted to the stable state and eventually settle at the bottom. An unstable steady state is kind of like a cup turned upside down. The stable state here is right at the bottom of the cup right here. If I place the marble exactly right there, then it will stay put. It will not move. The system state will not be changing. But if I place the marble anywhere away from that exact point, then my marble will fall off. It will run away from the unstable steady state. So those are my two sort of go-to analogies. This is a stable steady state here. This is an unstable one. In the last example in the previous class, this 4 is a stable state because that's when the derivative is actually equal to 0, and it is a stable one because here we can see that points actually get attracted to it. We also notice that arrows come in handy because for a stable state, they point toward it. I can see that, as I was talking about in the last lecture, if I place an ant here, the ant will crawl in the direction of the arrows, and it will in fact crawl toward 4. So I would like another notation to be able to distinguish the equilibria on my phase diagram as stable and unstable. So here is what we're going to do. On the phase diagrams, we're going to introduce a very small notation. We will use a filled-in circle for stable, steady state, or equilibrium. And we will use an open or hollow circle for unstable equilibrium. And again, on the slope field, we're going to be looking at where the solution leads us. And on the phase diagrams, we're going to be looking at arrows. Let's do another example where we draw both a phase diagram and a slope field with our new notation and with identifying the stability of the steady states. So in this case, we have y prime is y times 1 minus y. We're asked to sketch both a phase diagram and the slope field. Once again, please note that on the phase diagram, we have y versus the derivative of y, whereas on the slope field, in terms of the axes, we have time versus y itself. So the slope field will provide us with solutions. The phase diagram will describe the behavior of the actual derivative as the differential equation relates the two. So let's start with the phase diagram in this case. So first of all, on the phase diagram, I will be drawing what the differential equation tells me, with y being the variable that corresponds to the horizontal axis and y prime being the variable that corresponds to the vertical axis. If it makes it easier, think of this y on the right-hand side as your x value, as you would normally treat it to be a horizontal axis. Okay, so this y corresponds to x, and this y prime being the vertical axis will be what normally in our pre-calculus and calculus 1 graphs corresponded to the vertical axis. I can open up the brackets, but before I do, having it in factored out form will actually be easier for finding stable states. Recall that stable states are always the points where the derivative is 0. So I'm simply going to be setting this derivative to be 0, which means I set the right-hand side of the equation to be 0, and I'm looking for solutions. In the factored out form, it's easy to see that because it's a product, either of the two things has to be 0. So I'm going to get y equals 0 and y equals 1. Those are my two steady states, or equilibria, whichever way you prefer to call them. Now, finding them is one thing, but deciding which one is stable or unstable, or whether they're both stable or both unstable, you will have to actually draw the phase diagram for that. Algebraic techniques are not going to be helpful in determining the stability itself. So we are going to next have to draw what this looks like on the phase diagram. Stable states correspond to the derivative being 0, which means that they are going to be where the graph intersects the horizontal axis, and that is at 0 and at 1. Because I can see that my scale here has to be a little bit bigger, let me say the 1 is over here. So I know my graph will have to go through these 2 points. Now, I can open up the brackets to be able to tell the shape of the graph a little bit easier. So if I open up these brackets, y minus y squared, I can see that what I have is a quadratic equation, which means it's a parabola, and there is a negative coefficient in front of y squared, which means it's an upside down parabola. If it has to go through these 2 points, I know that the maximum will occur exactly halfway in between, so I can sketch my parabola shape fairly accurately, like this. This is now the graph y minus y squared, where y corresponds to the horizontal axis. I can do even more than that because I know that this happens halfway between the intercepts of a parabola. I can plug in a half into my equation to figure out how high this point is. And plugging in a half, I will see that this point actually corresponds to the derivative being a quarter. Now, let's recall how we place arrows on our phase diagram. If the graph is below the x-axis, the arrows go to the left. They indicate that if the graph is below the x-axis, that means that the derivative, which is our vertical axis, is negative, and therefore the solution should be decreasing. So the arrows point to the left. When the graph is above the x-axis, which happens to be on this entire region here, that means that the derivative, which is our vertical component here, is positive. All of these have a positive derivative, which means that the solution is increasing and the arrows have to be pointing to the right. Now you can draw as many arrows as you're comfortable drawing. 1 or 2 usually should do the trick per interval. Then after 1, I can see that my graph is below the horizontal axis, which again means that for the points here, the y prime is negative, and therefore the arrows should be pointing to the left. So again, remember, let me write this down here one more time. If the derivative is negative, then the arrows are pointed to the left And if the derivative is positive, then the arrows of the phase diagram are pointing to the right. Now, once you've drawn the arrows, this is the thing that lets you decide the stability of the equilibria. Let's take a look at this equilibria. There's two of them, 0 and 1. This one, you can see that the arrows run away from it, which means that if I start my little ant over here, the arrows will lead it away from 0. This signifies that 0 is an unstable steady state, and therefore I am denoting that by an open circle on the phase diagram. For 1, though, I can see that arrows point toward it from both sides, which means that if I place my little ant near 1 here, the arrows will lead it toward 1. That means that 1 is a steady state, or stable state, steady state, which I denote by a filled-in circle on the phase diagram, and I can then state that as a conclusion to my stability analysis. So let's just review the process. I'm going to draw the differential equation on the phase diagram with y corresponding to the horizontal axis. I will set the derivative to be 0 to find the equilibria, but I then have to draw the phase diagram and the arrows to determine the stability of said equilibria. Phase diagram is really useful for determining the stability of steady states, but it does not give me an idea of the shape of the solution. This is what the slope field is good for. Again, it is time consuming to do it by hand, and you might be able to find various graphing calculators that will lead you to construct slope fields for you from scratch, but we're going to do it by hand a couple of times just to get the hang of it. So once again, for the slope field, all I have to do is actually figure out the slopes that the differential equation tells me. Again, recall that differential equation is telling me what the derivative is, which means that the left-hand side here is actually the slopes of the tangent lines. In this equation, the right-hand side only has y values, so I'm going to pick a variety of y values to plug in to calculate the slopes for. Let's say I'm going to plug in 0, I'm going to plug in, for example, a half, I'm going to plug in a 1. Having sketched the phase diagram, I can already see that 0, 1 are going to be important points. Somewhere in the middle here is going to be important, and maybe I want to plug in a number that's slightly bigger than 1, let's say a 2. So for each one of these, I'm going to compute the value of the derivative that the differential equation is giving me. Whether you plug it into this form or this form, doesn't matter whatsoever. So if I plug in y equals 0 for y on the right-hand side here, I'm going to get 0 times 1, which of course means 0, so y prime is 0. If I plug in 1/2 into my equation here, same as here, 1/2 will actually give me a quarter. So y prime here is equal to a quarter. If I plug in a 1 into here, I'm going to get 1 times 0. So for this, y prime is equal to 0. If I plug in a 2 into here, I'm going to get 2 times 1 minus 2. So 2 times -1 or minus 2. Let's now sketch this information on the actual slope field. So notice, just like in one of the examples we've done before, that here, the right-hand side of the equation doesn't depend on t at all. It only depends on y itself, which means that this information here is now going to be consistent no matter what t is. So let me draw these slopes for some value of t and then extend it horizontally for all t. So what do we have? For y equals 0, I have that y prime is 0. Y equals 0 on this axis. So for 0, I'm going to have a horizontal slope right here. For y equals 1/2, now notice my actual scale here. For y equals 1/2, let me maybe decide that this is going to be where 1 is. Then 1/2 is over here, and I have that the slope is 1/4. So 1/4 is going to be a slope that looks something like this. At 1, I am back at the slope equals to 0, so completely horizontal. And at 2, which is somewhere up here, I have that the slope is a -2. So up here, it's going to be -2. In fact, it's going to be quite a bit steeper than that. Notice that this is not really quite enough information for me to really sketch the shape of the solution. So it would be better if I plugged in more numbers in between. If I plugged in, for example, a quarter, 1/3, and so on, as well as 2/3 or 3/4 and whatnot. If you plug those in, you will notice that the slopes go from 0 to 1/4. They increase slowly. So at first I'm going to get flatter slopes, and then they're going to increase up to 1/4, and then after 1/2 they will decrease back to being flat. Okay, something like this. There we go. So now again, these will hold no matter what t is, which means that this entire picture can get replicated for all values of t. I'm going to take this and I'm going to copy for all t values. Okay, so this will continue all in this direction. And then I can think about what that means for what my solution curves will look like. Okay, and I can see that in terms of solutions, if I start somewhere down here, my slope will be increasing. At 1/2, it will be the steepest it's going to be, and then it's going to decrease towards the flat point at the equilibrium at 1. If I start in the top, I'm going to decrease all the way to my stable solution at 1. In either way, I can see that from the bottom, I am converging towards the stable state of 1. So if I start here, my arrows will lead me toward 1. And if I start above 1, I will converge towards 1 again. So I start above 1, my arrows will lead me back toward 1. This again highlights a very important connection between the phase diagram, where the height represents the slope value that is what we are sketching on the slope field. The slope field, once again, will give us the general shape of a solution. The phase diagram, though, will give us the stable states and their stability. This equation, being quadratic that it is, and particularly being actually written in this form, is very reminiscent of the logistic equation we've already seen. And in fact, instead of drawing this by hand, let's take a look at what it would be like if I drew it with a software. This is the slope field that corresponds to this equation. If you extend this out and compute a bunch more points in the middle, these are the little slopes that it will produce. So this, in fact, is the slope field for the equation y prime is equal to y, 1 minus y. These are the exact same thing, just repeated twice, so I can draw on both of them. Now, let's see what this question is asking. This is really keeping the actual y prime sort of hidden and is only given to us by the slope field. But again, because this is from a previous example, I happen to know its formula. We have to decide whether these things are true or false for the given slope field. So let's go through them one by one. A solution y of t cannot have a local maximum. Is that true or not of the given slope field? Now, we are asked about the solution, so that means that on the given slope field, I actually have to draw in some solution curves. Let's draw them in for different starting points. If I have an initial condition that starts here, I have to follow the shapes of the tangents of the slopes that I have actually drawn out. So if we start down here, if I want to keep my curve tangent to the slope curves, slope lines that are sketched, I will produce something like this, right? So if we start down here, I will have to follow these guys and produce a solution that looks like this. If I start higher up, so for example here, I notice that it immediately increases and the shape is slightly different than the one I've produced before. If I start at the top, then my solution simply decreases toward the steady state. And if I start below 0, I notice that the slopes lead me away from 0 altogether. This also immediately indicates to us that, first of all, it should have been obvious from the slope field right away that 1 and 0 are stable states, but only once you start drawing in the solutions, you can see that solutions run towards 1, which means that this is a stable steady state, and solutions all run away from 0, which means that 0 is an unstable steady state. So let's go back to the question here. A solution cannot have a local maximum. Well, it looks like I have drawn all the possible solution curves here, and indeed, none of them have a local maximum. None of them go up and then down again, forming a local peak at the top. So this appears to be true. The next question says, if y1 and y2 are two different solutions, then they cannot cross. Let's think about this in general. This actually doesn't depend on a given slope field. This is probably something that we can generalize about. If there are two different solutions, they cannot cross. Let's think about what would happen if they did cross. What would the intersection look like? So if I have one solution going one way and a different solution going a different way, what happens at this point? What is the tangent at this point? As far as my purple solution is concerned, here the tangent has to go this way. As far as my blue curve is concerned, blue solution is concerned, the tangent has to go this way. Well, I cannot have two different tangents at one point because that would mean that there is no actual derivative that exists there. Moreover, as you see on the slope field, none of the little lines that I drew could possibly have two different values at the same point. I determined the values by plugging it into the equation and getting a unique answer. For this to happen, the function would have to be not differentiable at that point, which means I wouldn't be able to even follow the actual differential equation. So this is true of any slope field. If you have two different solutions, they cannot possibly cross. This is absolutely true. Now, the next two do concern this particular solution and this particular slope field. If I have a solution y of t, then if y of t is a solution, then so is y of t plus c. This, you have to remember what this corresponds to in terms of function transformations. Y of t plus c, adding the c in the middle to the argument or outside will produce two different function transformations. Outside produces a vertical shift, inside produces a horizontal shift. In this case, we're not told whether c is positive or negative, so I have to think about horizontal and vertical shift in general. Let's think about horizontal shift first, so this guy right here. If I have one of these as solutions, then if I have a horizontal shift in the function, will that also produce a solution? So let's say I start with this solution here. If I shift this graph horizontally, is this still a solution? Yes, it looks like it. In fact, this is exactly how we build the slope field in the first place. Notice how every column here of the slopes looks exactly the same, because remember that this differential equation did not involve t, which means that once I've constructed the slope, it was to be copied for all values of t. So this is true. What about a vertical shift? So once again, if I start, let's say, with a solution like this one here, let me draw another one next to it. If I shift it vertically, will what I have still be a solution? Well, no, it's very clearly not true because this new curve does not at all follow any of the slopes that have already been drawn out. So this last one is false. Do note that only number 2 applies to any slope field, and the other 3 points here are specific to the slope field at hand. So this particular differential equation and this particular slope field. Let's look at another slope field example. So in this case, we are given a slope field and we're asked which one of these differential equations matches this slope field. Slope fields have a lot of information, and we just have to unpack it to see how we can match it to what is presented in the differential equations. First of all, looking at the slope field, a few things are noticeable. I can see which are the equilibria for this particular differential equation, and that is going to be when the derivative is 0, which means the slopes are in fact horizontal. I can see that the slopes are horizontal at 1, and I can see that the horizontal slopes are also there for -1. So these are my two equilibria. I can also classify them as stable and unstable depending on the slopes, whether they lead toward the equilibria or away from it. If I am to sketch solutions here, so let me first of all maybe sketch in a few of the solutions. If I start here and follow the curves, I will go up. I can see that this is my equilibria here, or equilibrium. If I start over here and follow the slopes, I am going to go in this general direction and toward my second equilibrium here. And if I start at the bottom, I will simply converge up to it. So I can see, based on the slopes, that 1 is unstable equilibria because the solutions run away from it. This is unstable, whereas -1 here is when the solutions come toward it, which means that this is in fact stable. I have two equilibria at 1 and at -1, which means that whatever differential equation matches the slope field has to have only 2 points at which it's equal to 0, 1 and -1. If I set this to be 0, I notice that I'm going to have y equals 0 or y equals -1, but y equals 0 is not a steady state in my differential equation, so this equation does not match my slope field. Take a look at the next one. If I set this to be 0, I will precisely get 1 and -1, so this is still a candidate for my slope field. Same with this guy here. 1 and -1 are zeros here, and therefore equilibria, which means that this is still a candidate. Whereas for the other two, I'm going to get y equals 0 as the steady state, which is not the case in this particular slope field. So these two differential equations are out. Now, how do I decide between these two? They have the same steady states, so I can draw a phase diagram to decide which one is stable and which one is not, but we can even do something a little bit quicker. Remember that the slope field gives me the slope value at any particular point I wish to compute it. And these two equations only differ in the negative here. So what I can do is simply plug in some number. Let's plug in some value. You can plug in any value really. The easiest one to plug in is probably 0. So if I plug in 0 into the equations for 2 and 3, what am I going to get? The equation for 2, if I plug in 0 into the right-hand side here, will give me -1 times 1, so -1. And the equation 3, if I plug in 0 here, will give me negative of the same thing, so +1. Now let's see which one of these matches my slope field at y equals 0. Y equals 0 is the horizontal here, because remember that this is y prime and this is values for y. So y equals 0 are all of these slopes here that are all the same. So this slope right here, does that look like a -1 or a +1? Well, it's pointing down, it's decreasing, so it's most definitely negative. Independent of what the actual value is, it has to be a negative number, which means that the second equation, is my only potential candidate. This question is very similar to the ones that we've done before, so I'm going to leave this one for you as an exercise. It's a linear differential equation, so it should be fairly straightforward to do. I'm going to do a very similar question, but for a cubic one, so more complicated. So let's go through the examples here. We're asked to determine the steady states, sketch the phase diagram, and determine the stability of the steady states. Notice that if you are simply asked to identify the steady states and determine their stability, then the first two parts are the mechanisms by which you have to do that. And afterwards, we're simply asked to analyze, based on the initial state, what is the eventual behavior of the model. So let's do this from the top. My differential equation is cubic, y minus y cubed. So in order for me to determine the steady state, I am going to think back to what does it mean to have an equilibrium. An equilibrium is where the derivative is 0. So I'm setting my derivative, my right-hand side here, to be 0. I now have to solve this cubic equation. I notice that I can factor out one of the y's, and I have y times 1 minus y squared, which means that my steady states are y equals 0 from this bracket, or y equals plus or minus 1 from the second bracket. I have 3 equilibria in total, and now I have to sketch the phase diagram in order to identify their stability. Now you have to decide on the scale based on the steady states you're given. A lot of times we will be working with models where the values will only be considered to be positive because of the context they're in. But in this case, I have that my steady states are 0 and plus and minus 1. So I'm going to draw a full picture of that. So I have -1 and +1 here, and I have to decide how the graph looks like. Let's take a look at the original, y minus y cubed. Here, the power domination analysis is going to be extremely useful. So recall that for small values of y, the smaller power dominates. So for small values, I'm going to have that my graph resembles y, which is, of course, a line of slope 1. So I have something that looks like this. Whereas for large values of y, the higher power dominates. So my graph for large values of y will have to look like minus y cubed. So it's important here to remember that the coefficient has to go with the domination. Y cubed looks like this snaky shape here. Minus y cubed will look like the snaky shape in the positive direction. And I have to take this graph only for large values of y. So somewhere at the negative infinity and somewhere at the positive infinity. I now have to connect these 3 pieces of my domination power analysis, as well as the 3 intercepts that the graph has to go through. There's basically only one way where this is going to happen, and that is if my graph goes through -1, turns around, goes through 0, comes back around, goes through 1, and goes down to match my original shape from the dominating power analysis. Once I have this, it's time to put on arrows on our graph. Let's remember that what I have is, if my graph is above the x-axis, my arrows point to the right. If my graph is below the x-axis, my arrows point to the left. So if the graph is above the, not the x-axis, it's really, I should be labeling these. This is my y, this is my y prime, the horizontal axis, I should be calling it. If the graph is above it, the arrows point to the right. If the graph is below it, the arrows point to the left. If the graph is above it, then I go to the right again. And if the graph is below it, which is the case on this last region, then the arrows once again point to the left. Now I simply have to follow the arrows. These are my equilibria. Let's take a look and think about what happens at each one of them. At -1, the arrows converge toward it, which means that this is a stable steady state. At 0, I notice that the arrows always point away from it, which means that this is going to be unstable. And at 1 again, I notice that the arrows point toward it, so this is once again going to be a stable steady state. You can write this as an actual sentence conclusion, or you can carefully label it on the graph with filled in circles being stable and a hollow circle being unstable. I strongly recommend doing both because sometimes drawing circles can be a little bit tricky. So do write it out fully. This is going to be, let me split these guys up. So I have y equals 1, y equals -1, and altogether I have that 0 is unstable, but these both are stable. The next questions all ask about what the solution tends toward as time goes to infinity, so as time goes on, depending on the initial condition. It can be handy to have a slope field for this, but we can also actually get this information from the phase diagram. If the initial condition is -1, so if I drop my little ant onto the horizontal axis at -1, where is it going to eventually end up? Well, -1 is a steady state. So if the ant lands directly on -1, it's never going to leave. It's already a steady state, so it's going to stay there forever. This limit is going to stay at -1. What happens if the ant starts at -0.9, so somewhere over here? Again, it follows the arrows. The arrows on this region point to the left because the graph is below the x-axis. So if it starts anywhere over here, it's going to be pushed towards -1, which is in equilibrium. So once it's there, it's going to stay there. The eventual behavior will be ending up at -1. What if we start at 0.9? So somewhere over here, then the arrows on this region are pointing to the right. So the ant, or your little point, will be pushed towards 1, which is a steady state, and it's a stable one too. So once it's there, it's going to stay there. What happens if we start at 2? So somewhere out here. The arrows in this region point to the left, so we will eventually move toward the steady state at 1 and stay there. Let me include one more question here that usually is a little bit tricky because it's hard to perceive that. What if, number 6 here, what will happen if I start at 0? What is the eventual sort of resting point for this ant? If it starts at 0, it is an unstable steady state, but it is still a stable state, or a steady state, which means that if you start here, you will not move away. If you start even a little bit off of 0, then you will move further and further away. But if you start at 0, you will stay at 0. It's an important distinction. Remember that stability of steady states is describing what happens if you start away from it. But the equilibrium itself means that if you land on it, you will stay there, independent on whether it's unstable or stable itself. Let's take a look at our first real application here, population disappearances. We will use an example of queen conches in the Bahamas that have been threatened by overfishing. They are an important food source for large predators such as sharks and turtles, which means that their disappearance also affects other species. This differential equation describes their disappearance rate fairly closely. This is modeled on real data. And what we normally would like to do is introduce some kind of a variable, or rather parameter to it, that we can model around. This models the annual harvesting rate. So what we would like to do is figure out how many queen conch can be harvested by humans without affecting the overall population size. What the question here asks is to draw phase lines for different values of the annual harvesting rate and then discuss biological implications for each one. Now, we can, of course, plug in one value at a time and draw the phase line one at a time, but let's try to be a little bit more efficient about it. So what I'm going to do at first is rewrite this by opening up the brackets. So what do we have here? I have y prime is equal to 10y, and then 10y times y over 10,000, which means that it's going to be minus 1 over 1,000 y squared minus a. What kind of shape is this if I were to draw an actual phase diagram. I have a parabola here, a parabola facing down, and this minus a really corresponds to a vertical shift. So let's note that this is a parabola, this is a vertical shift. So instead of drawing 3 different phase diagrams for the exact same model, I'm actually just going to draw one and try to think of how to implement this vertical shift onto it. So let's sketch this out. I'm going to, again, as the phase diagram would, draw the 2 axes that each correspond to y versus y prime, and then draw my actual parabola. The base parabola I'm going to draw is going to correspond to a being 0, and then we will mark other shifts on our graph. If a is equal to 0, or rather, it's easier to look at it in the factored out form, if a is equal to 0 here, I can see that my parabola will have the horizontal axis intercepts at y equals 0, which will correspond to this term being 0, as well as y equals 10,000, which will correspond to this term being 0. So let's label this to have units in thousands. And I know that I will have 2 intercepts at 0 and at 10,000. And overall, my parabola, maybe I will mark a 5 for the midpoint, and therefore the vertex of the parabola will look like this, right? Again, remember that this is just an upside down parabola shape. I can, of course, compute, I can plug in 5 into this equation for y, 5,000. Remember that I'm drawing for a equals 0, and I can compute how high this point actually is. This will turn out to be 25 here. So this is now the general sketch of the phase diagram that corresponds to a equals 0. So this is a equals 0, no vertical shift. Now you got to imagine what is going to happen to this graph for a equals 21,000. Now we're drawing in thousands, so that means that a is 21. If I vertically shift this parabola minus 21, so I'm taking this parabola and shifting it down 21 units. The other way to think about this is either I'm shifting the parabola 21 units down, or I'm really shifting this horizontal axis 21 units up. So because that is easier to draw, this is what I'm going to do. If this corresponds to a equals 21, then my horizontal axis will be here. If I have to draw the shift of a equals 30,000, I will be shifting my original parabola 30 units down, or shifting my horizontal line, or horizontal axis, 30 units up. Now notice that my A's are probably not up to scale here, but I would like to actually note the overall shape, not the exact scale of it. Okay, and so what I have now is this is a phase diagram for a equals 0, this is a phase diagram for a equals 21, and this is a phase diagram for a equals 30. Let's determine the stability of the steady states, if there are any, for each one of those, and discuss their biological implications. So for my original a equals 0 phase diagram, I have this is a line, and this is as my actual differential equation. So I notice that my 2 steady states are here and here. If I introduce arrows, when it's below the x-axis, the arrows are to the left. When it's above, the arrows are to the right. And then after 10, the arrows are to the left again because the graph is below the x-axis. So I notice that 0 is an unstable steady state and 10 is a stable state. Stable states in populations are good to have because that means that if my population starts below 10, it will grow toward 10. If it starts above 10, it will grow down to 10, but my steady state is at 10,000 queen conch, which means that the population is stable at that particular number. Whether it's growing toward that number or decreasing toward that number because of scarce resources, it's going to have 10,000 queen conch as the population that it approaches. When a is equal to 21, I have this as my phase line and this as the graph that corresponds to it. So let's mark this portion with the arrows. This is now my main horizontal axis. When the graph is below it, the arrows are to the left. So my red arrows here will go to the left. When the graph is above my current axis, which is red, which is right here, the arrows will point to the right. And when the graph is below my red axis, the arrows will point to the left again. So notice that here I have an unstable state that is somewhere. I can probably figure that number out, but I don't have to yet. And my steady state lies here. So I still have a steady state for the population, a stable steady state for the population, but it's now less than 10,000. Notice that this one is more to the left. So the population can survive and be approaching some number, but it's not going to be as high as 10,000 as it was before. For a equals 30, I now have this as my phase line and no graph at all to even think about. So I can't have any equilibria on this line at all. There's no equilibria here. The population here does not survive. This is the situation of overfishing. In fact, by moving the phase line up this way, we can see that up until I hit 25, I at least have some steady state that the population can approach that is not zero. Once your phase line is above 25, or your annual harvesting rate is above 25,000 queen conch, there are no steady states at all, which means that the population will not survive anything over 25,000 units being fished out. We can analyze the queen conch example purely from the formula itself, but it will be a little algebra heavy. So I'm going to go through this for completeness to confirm the graphical information, but this is not the type of calculations that I expect you to do in full for examples like these. So let's think about, given the formula, how does equilibria depend on this harvesting rate A? Again, equilibria is where the derivative is equal to 0, which means that I have to set my equation here to be 0. So I need to have that 10y 1 minus y over 10,000 minus a is equal to 0. And I need to solve it for y. I have this parameter a here, which means I cannot simply try to find numbers that will work. So the only way to actually solve this is to apply quadratic formula. I'm not going to go through the exact steps of the quadratic formula. This is fairly straightforward. I will simply record the result. The result of the quadratic formula will be that y equals 5,000 plus or minus 100 square root of 2,500 minus a over 10. So I notice that my parameter a is present here at the end. Let me actually highlight it in a different color. There we go. So how can I determine the values of y depending on the values of a? Well, I notice that there is a square root here. And in fact, normally quadratic formula will produce either no solutions if the number under the square root is negative, one solution if the square root is 0, and two solutions if the square root is something I can actually compute with. And this is exactly what we're going to have here. You will have two solutions and therefore two equilibria if the value under the square root is positive. We have two equilibria if 2,500 minus a over 10 is positive. Now, if I actually solve this for a, so move things over, multiply by 10 and whatnot, this will be the same as having a less than 25,000. We will have one equilibrium if the value under the square root is exactly equal to 0. Because if this is equal to 0, this entire term will go away. I won't have to worry about plus minus, and my equilibria will be 5,000. This corresponds to the A value being equal to 25,000. And we will have no equilibria, no stable states to even think about if the number under the square root is in fact negative. And that corresponds to A being bigger than 25,000. Let's take a look and see if this analysis agrees with what we had on the graph on the previous slide. I had two equilibria. If A was less than 25,000, less than this peak of the parabola here, no matter where I drew the line before that, I would have 2 points. The equilibria will be different every time, and in particular, the higher equilibria, the stable one, will get smaller and smaller as we go along, but you will always have 2 of them. At 25, if I draw a phase line here, I will notice that it just touches the parabola, and this will in fact produce an unstable equilibrium at this point. But anything above will have no equilibria at all. And that is what corresponds to high harvesting rate and the population not surviving. This is the graphical and the algebraic way to analyze models with parameters.